Okay, so thank you for coming today, those of you who made it. It's not a great day for scheduling, I know, but hopefully it's difficult teaching on this day, the morning before Thanksgiving, because a lot of people try and travel today, and the sooner you can get away, the better it is. So typically the turnout is less, but we got stuff to get through, so I can't really not include stuff, but hopefully people will be able to see this one way or another. So where are we? We are a lot of the way through. We've just finished the FIR filter design. That was like our main content for the second half of the semester, which was how to actually design filters, looking at the tools and the processes for building the filters of the, using the principles we'd learned in the first half of the semester. So all we have now remaining is some stuff on the fast Fourier transform. So this is looping back to the DFT and this particular algorithm for calculating DFT very efficiently, which is interesting in its own right because it's very, very sort of unexpected, I guess, trick for drastically reducing the computation to calculate the DFT. And it has huge impact because it basically means that we can think about processing things in the frequency domain by doing a Fourier transform, then processing, then doing an inverse Fourier transform, and that's not like a crazy, inefficient way of doing stuff. So we'll talk about that, and then we'll talk about the short time Fourier transform, which is the same thing, but doing it on little short windows, which is actually a somewhat practical way for actually processing signals as an alternative to straight time domain implementations. And then we'll have one lecture just talking about some of the issues interfacing to continuous time, thinking about how we got from continuous time to discrete time and what the impact of that is. And then that's just one more class. We'll have the project presentations. I've had, I think, 5 or 6 volunteers. That's pretty much all we can handle. But if you do still want to do a project presentation, please send me an email as soon as possible. I'll be sending out an email this week confirming the people who I'm expecting to present. Final exam after that. This is also the nominal due date for the project reports. Any questions about that? Schedule for the rest of the semester. Okay. All right, so the fast Fourier transform. We've used the frequency domain, we introduced the frequency domain, we've used it as a way of analyzing and designing filters. Very often the operation we want to do, we can think about it in the frequency domain. There are certain frequency ranges or frequency components that we're trying to manipulate. But then what we do with it is we simply figure out what the frequency or the transform domain, like the Z-domain description of a system would be, and then we implement it in the time domain. So by taking our rational polynomial, turning it into delays, and then just implementing it. But in a way, if we've sort of gone to this effort of describing what we want to do in the frequency domain, if we had the signal represented in the frequency domain, we wouldn't have to do filter design at all. We could just directly manipulate it. And then maybe that would be enough. Maybe we're working in the frequency domain, or maybe we could then just convert it back. So you could imagine a style of processing like this, where you start off in the time domain, in the discrete time domain. You convert it in the Fourier transform now, convert it in the Fourier domain. Now, because we're talking about an actual real system, the Fourier transform we'd have to use would be the DFT, mapping from a finite length time sequence to a finite length frequency domain sequence, because that's the only one we can directly represent in a computer with finite amounts of memory. So we take DFT, get our x of k, now nice finite order representation of the signal in the frequency domain, modify directly the frequency domain terms to give us a modified signal y of k, and then finally take the inverse DFT to get back to the time domain signal. This is very appealing if we're used to thinking about, if we've developed our way of thinking about signals in the frequency domain. It's a little bit deceptive because, of course, x of k, remember all this discussion we had about the difference between a truncated signal and a periodic signal. It's not quite what you think. It may not be quite what you think it is. On the other hand, this is quite feasible and can be pretty effective. The idea that we have to get all of x of n in before we can do this can be a big problem. But we can also do this by chopping a longer signal into shorter windows and then doing this on each short segment, which would be the short-time Fourier transform approach. And that has its own catches, but again is quite feasible. But the big obstacle to this is these two steps, the DFT and the IDFT, because typically they would involve a lot of computation, and particularly as the length of the block that we're converting into the frequency domain, which is equivalently the frequency resolution that we have, as that gets larger, then the DFT gets progressively more and more expensive. So what is the DFT? Well, here's the DFT equation we had before. It's just, to get big N frequency samples, we take big N time samples, and then for each frequency sample, we multiply it against this constant Wn raised to the power k times n. Wn is negative, it's this, e to the minus j 2 pi on n, so it's 1/n of a revolution going in the negative direction. Now, and we're going to raise it to a lot of different powers up here to multiply multiply against x of n to form the DFT terms. Because Wn is exactly 1/n of a revolution, when we raise it to powers, this is Wn, this is Wn squared, Wn cubed, we're sort of going round the circle. When we raise it to powers greater than n, it wraps around, right? It's basically a pure phasor. And because it's exactly 1/n of a revolution, there are only big N distinct values it can take on. So k times n can take on a lot of different values, but a lot of them will be the same as other values because there are only big N points around here where this thing can end up pointing. So that's one reason, okay, maybe there's some redundancy or some structure that we can exploit to try and reduce the computation. This summation form is the same as this matrix form. This is just writing out each value of x of k each as a function of, as a matrix multiplication times each value of x of n, little x of n, and here are the coefficients. So this is, this is w sub n to the kn, where the row is k and the column is n, right? So we just have these exponents here are those kn values. And when we write it out like this, again, we see a lot of structure, that we see these anti-diagonal values which are the same. And so we can think about trying to, that again, it's just a hint that there may be some way we can, because, in here there are a lot of values which end up being the same, so maybe we can not have to calculate each one explicitly, but have some way of factoring the computation that will reduce the total number of multipliers we have to do. And that's exactly what the FFT does, but it's not obvious just by looking at it how to do that. So how do we measure what we're trying to save? We need to think about the issue of computational complexity in the Fourier transform. And basically, in any kind of any of the computers we're used to, the way you calculate this is you have a sequence of steps. Each step is something like a multiplication or an addition, and it'll take a certain number of times, take a certain number of clock cycles on the computer or whatever. Actually, depending on the architecture, or depending on in fixed point representations, multiplies are normally pretty the slow things. Additions are quick. You can normally do them with a single step, but a multiply is done by a repeated shift and addition. In floating point representations, it's the other way around. The multiplies are pretty easy, but additions require some normalization of the two floating point mantissa. And so anyway, so it's not clear which is worse between multiplies and adds, but multiplies and adds are the things that are going to take time. It's going to take us a certain amount of time. So we can just count up the total number of multiplies and adds that are involved in our calculation to get an idea of how much computation it's going to take, how expensive it's going to be. So this calculation, well, W sub n is, of course, a complex constant. So we're talking about complex multiplies and complex additions here. And here we've got, this is a summation, a big endpoint summation. Each one of these is a complex multiply, and then we have big N numbers which we have to add together. So it's n complex multiplies and n minus 1 complex adds for each x of k, for each k point we come out. So it's a total of this times n output points, which is basically going to be n squared. It's going to be order n squared, right? A complex multiply, typically our computers don't actually have complex as a basic numerical representation. The multiplier in the chip is going to take real valued numbers. So we have to calculate it in terms of actual real multipliers. So if this is the Cartesian representation of these two complex numbers, that one complex multiply actually works out to be 4 real multiplies and 2 additions to get our Cartesian parts back again at the output. And then the complex additions are just simply 2 real additions for the real imaginary parts. So finally, our endpoint DFT, calculated in this direct way, is 4n squared real multiplies and 4n squared minus 2n real adds, because we don't have to add, we only have n minus 1 adds for each value. Okay, but this is why as n gets larger, as the length of the DFT that we're calculating gets larger, the computational cost gets worse as the square of n. It's not just proportional. So if we want to have more frequency resolution, we have to pay an increasingly high price for it. Well, before we get on to the FFT, we're going to look at one other slight simplification. And this is not of tremendous practical importance, but it's kind of interesting just to show you the kind of thing that you can, the kind of tricks you can pull to try and reduce computation. So this is Goertzel's algorithm, and basically it's saying, well, if the individual x of k calculation is this, the sum of the x values times w sub n raised to that power, we can rewrite this like this. So we can take out a factor here. Then we get this, that ends up giving us this, where we've got x of L times some function of n minus L. And this is in the form of our convolution sum, right? The convolution sum is the sum, the inner product between x going forward and something else indexed backward. I mean, given that something else could be whatever we want, it's not a big deal that we can convert it into that form. But this is just suggestive. It's like, okay, if we had a filter whose impulse response was this, but read forward, then at some point its output would be the convolution of these two, and we could actually have this expression that we're trying to calculate be the output of the convolution of x with that system. So what we're saying is the actual x of k we want to get could be the output of some system at some particular time point. And in particular, if we set up y of k like this to be x with a 0 at the end, a 0 padded on the end, convolved with a system whose impulse response was this h of k, which is basically just the w to the minus kn values, then this convolution would give us this answer at time n, time big N. But this impulse response is basically an alpha to the n thing. So it's an IIR system with a single feedback term of alpha equal to w sub n to the minus k. So we can build a system with that impulse response very, very simply like this. Right? This is just, the first time it's 1, then it's if you put an impulse in, you get 1, then alpha squared, etc. So if we just set up this system where we feed in the signal that we want to get the DFT for, and we have this single one-pole filter, we just run it for big N steps, then we put in a 0 at the very last point, then, and we start off with, initial state of 0, then the output at time big N will be this x of k. I mean, it's kind of like you could, if you have any kind of inner product like this, you could imagine that it was the output of some convolution like this. The reason this is compact is because the impulse response we need to calculate is itself very, very easy to construct, just as this one-pole IIR. Okay, well that's curious, but why talk about it? Well, there are a few things that are nice about this. So, firstly, if we want to calculate some specific values of x of k, some specific DFT bins, but we don't necessarily want to calculate the whole DFT, well, this gives us a way to calculate each one individually. We just build one of these simple filters for each of the x of k's that we care about. Secondly, if we wanted to calculate the DFT, then typically what we have to do is we have to buffer up big N samples of the input x. And then when we've got them all, then we can run the inner product and get the result. At least that would be the natural way to do it. Whereas here, we've got just this single, this running system that's calculating x of, calculating the output of our filter at every time step. So there's no large memory involved. And similarly, if in the naive implementation we'd have to pick up all big N of our points, then have this table of big N coefficients, which we then take the inner product against. Here, we've just got one value, which is the single gain in the feedback loop. So there's no large table of coefficients. In both of these, you could sort of, once you realize you can do this, you could work around them in your DFT naive implementation as well. But at least it indicates that, okay, we don't need to buffer up all N values, and we don't need to separately store each of those big N coefficients. But for all that, it doesn't actually save us any calculations. If you work it through, you still need the same number of real multipliers and real additions to calculate the final each value of x of k. There is one trick we can do to reduce the number of multiplications involved. This is the overall transfer function, the z transform of that system, right? It's just 1 over 1 minus alpha z to the minus 1, where this is the alpha. If we multiply top and bottom by the conjugate of this pole, basically we introduce a 0 and a pole at the at alpha. Sorry, not the conjugate, but the reciprocal of this pole here. Then we can actually get this thing to be, the conjugate. I do mean the conjugate. We can get, so this is, note this is a slightly weird filter, right? It's a filter with a single complex pole. So it's a complex filter, meaning that the impulse response is complex and the intermediate values we'd have to store would be complex, which is why we end up with so many multipliers here. But if we introduce the conjugate pole here and then cancel it with a 0 at the same place, then this becomes pure real. Now we have a second order. We have two poles, but they're conjugates, so the calculation becomes just real numbers. And then we don't have to deal with these complex multipliers and adds for every step. These ones just become real values. Assuming we have real valid input, then we just have real arithmetic. This thing, of course, is still complex because the final output we want to get, the x of k, needs to be complex in general. A DFT value will be complex. But this is just a one-point FIR. It's just x of n, or some intermediate value w of n, minus this complex constant times w of n minus 1. What we can do is we can calculate the intermediate values using the second-order system, and then and these just have feedback, right? So this would be just like calculating w of n and feeding back. And then we have this output here, which has got the feed-forward part. We only calculate this for the very last step. It doesn't matter what the actual output is, because if we have our state being fed back, then we can just calculate that, and then when we get to the end, we calculate this. So basically, we can cut this down to be only real multipliers, and that basically halves the number of multipliers and adds that we have to do, because for the bulk, for the big n minus 1 steps, we only do it in the real domain. So this is kind of, I don't know how to generalize this, but it's kind of a clever, it's an example of a clever trick to get around calculation, to get around computation by converting a problem into a pure real problem. So, that's something you can do. But all we've done in the end is halved the number of calculations here, which is nice, but it's still growing as the square of the length of the DFT we're trying to calculate.
So I don't understand. If we started out with calculating the Fourier transform.
Yeah.
And we do that with a computer, right? But how does
Yeah.
it relate to a filter?
Yeah. That's the point of this slide. So why we're calculating the Fourier transform, but now you're saying I'm putting a signal through a filter. What do you mean? I'm thinking of the DFT as a system, a box, where you put in a signal x as a function of time, and you get out a bunch of outputs, which are the values of the DFT, the values of the DFT for that signal, right? So you can imagine, this is, right, our filter is something where we put in x of n, we have some thing here, and we get out y of n. Okay, in general, we get one value out for each value put in. But now I'm having this particular box such that at some particular time, I get a value that I want here. So we're saying that, well, y of big N is going to be equal to x of k for some, which is just, so this could have been anything. Let's call it x sub k, right? Some value that we wanted, which is a function of these input values here, but it's just some particular feature. But it turns out that because we can define xk as the inner product between x of n and some other set of coefficients, right? The inner product, the point was multiplication and summation. Then if we build a system in here whose impulse response is those set of coefficients, then a linear system will calculate a convolution, which is an inner product between the input and the time-reversed impulse response. And so we can build a system such that y of n gives us this x of k at a particular point. So that's why we've built we've implemented a filter, but what it's giving us is the DFT values. And I guess there are a couple of weird things about that, but one of the weirdest is this is the first time we've actually seen a filter where we want the output to be complex. The input is real and the output is complex. Like normally, we'd never want that because it wouldn't have a physical meaning. But here we're specifically trying to calculate something which is a complex value, the DFT sample, and so we want a filter with complex output. That's actually kind of a nice little twist on that. Okay, great. Okay, so now the main event here, the fast Fourier transform. And the point is here, rather than having complexity that goes as n squared, we're going to come up with an algorithm that calculates the DFT, calculates the same thing, the full DFT, but in only order n log n calculations. And so that's a big deal because log n grows much less slowly than n, right? Log n is kind of this compressive function. And so as n gets larger, the gap between n squared and n log n becomes even bigger. And so for large n's, we can get something which is much closer to being just proportional to the length of the signal, length of the window, rather than the square of the length of the window. The way it works is by breaking down the big DFT into a set of smaller DFTs, and then at each stage saving computation. And it's so pervasive. It's so, there are so many different things you can do just by reducing them into a Fourier domain calculation, a Fourier domain representation, and some processing there, that this is a very popular algorithm, and anyone who's producing some kind of computational device will often spend a lot of time optimizing their FFT library so that'll run really, really fast, because it's like this nice way of modularizing what you're trying to do, to say, well, I don't want to do this stuff, but then I want to do an FFT. A lot of the computation is going to be the FFT, but so we can justify the time optimizing this because it's going to get used over and over again, and so we get that investment back. So there are a couple of ways of getting to the FFT, but here's the destination in time approach. There's a destination in frequency approach as well, but it's basically the same idea. And the idea is that we're going to split the full DFT calculation into two halves. And here's how we do it. Okay, so if this is the DFT calculation, the sum over little n equals 0 to big N minus 1 of x of little n times w sub big N to the little nk. If we consider these terms in this summation as a set of pairs of terms, x of n and x of n plus 1, or x of 2m and x of 2m plus 1 for all values of m, right? So if I have m from 0 to n on 2 minus 1, then this is going to cover all my x's. It's going to cover all big N of my x's. But now these are all the even indexed ones, and these are all the odd indexed ones. And then I keep these coefficients here. So it's x of 2m times w sub n to the 2mk plus x of 2m plus 1 times w sub n to the 2m plus 1k, right? This is the same summation. But now I can think of all these terms summed up and then all of these terms summed up separately. So all of these terms are just what they look like, x of 2m, w sub n to the 2mk. But w sub n is e to the minus j 2 pi on n. So w sub n squared is the same as, it's like 2 of those little 1 on n revolutions. So it's actually w sub n on 2. Right? We've sort of hidden that because we've not written out what it is. But if you remember what w sub n is, then you can see that if I've got everything which is raised to some even power, then it's the same as just w sub n on 2 to the mk. And now this is simply an n on 2 point DFT. It's some x sequence as a function of m, some sequence as a function of m raised to the w sub n on 2 to the mk, and there are n on 2 points here. So that's just the n on 2 point DFT of the even indexed values of x of the original sequence. Here is the other half, our odd indexed values. We can do almost the same thing, but we've got this w sub n to 2m plus 1. So we want to take this w sub n to the 1, take it outside. Then we get w sub n, then we're left over with w sub n to 2mk, which we can rewrite as w sub n on 2 to the mk. Here are values of x, which are now our odd indexed values of the original sequence. And here's the plus 1 that we had to take out. So it's w sub n to the k. But that's the same for all terms in the summation. So it comes out as a constant before the summation. And so this is now, again, just an n on 2 point DFT for a sequence formed as the odd indexed values of the original input sequence. We take that, and then for each value of k, we apply this constant here, w sub n to the k. We sum up those two terms. We can evaluate them for all values of k, and we get x of k out. The only weird thing here is that we're going to calculate this DFT, which is an n on 2 point DFT, for values of k from 0 up to big N minus 1. So we're going to calculate it for values of k larger than n on 2, which we don't normally do for a DFT. Normally we would only calculate n on 2 points. But it doesn't actually, w to some larger index just wraps around. So it doesn't hurt it. What happens is, as we calculate this for the second half of the second block of n on 2 points, it just repeats. Also for this one. So we have each of the n on 2 unique values of these two n on 2 point DFTs. We access each of them twice, but this value changes for the first half and the second half. So we do actually get different values. We get n distinct values for x of k, but they're composed out of these two sets of n on 2 distinct values for the n on 2-point DFTs, but with a different constant in here. So the constant is important, the scaling term here. But basically, that's kind of interesting that we've broken it down into two halves, and it works out to be exactly the same thing. But so here it is, written with this sort of DFT sub n notation here. So saying the endpoint DFT of a sequence x of n for little n equals 0 to big N minus 1 is the n on 2-point sequence of the something x0, which I'm just defining as meaning the even indexed values of the n on 2-point sequence, which is the even indexed values of x of n, plus the n on 2-point DFT of the odd indexed values with this scaling constant in here. So we calculated an n-point DFT with two n on 2-point DFTs, but we said the computational complexity of calculating an n-point DFT is order of n squared. So the computational complexity of an n on 2-point DFT is the order of n on 2 squared, which is a quarter of the order of n squared, right? I mean, there's going to be some constant in here depending on the algorithm, but the overall complexity is, because it goes as n squared, if we halve n, then the overall complexity is reduced by a quarter to 1/4. Now, of course, we had to do two of these half-length DFTs, but even 2 times a quarter is still only half of the calculation of doing it the full way. So by breaking into 2 of these, because the calculation is as the square of the length, and we just have to break it into 2 half-lengths, then the overall gain is halving the calculation, apart from these multiplications here, which are, there are n of these, but the n squared term which is the largest, going to be the largest term in the number of calculations, is halved. So that's pretty good. That's what we got with our, crazy Goetzel trick. We were able to halve the calculations, and so, here's another way of doing it, which is nice, but we already knew how to halve the calculations. To sort of think about what we're doing, it can be helpful to draw these flow graphs. So here's the expression right now. I'm just writing it in terms of x of k as these big X of 0, which I'm defining as the n on 2-point DFT of the even index values, and big X of 1 as the n on 2-point DFT of the odd index values. And here's the scaling factor, which is generally referred to as a twiddle factor. And so here's a picture of how we could find each big X of k for every value of k for an 8-point DFT using these 8 input values for an 8-point X of n. So here are the even indexed values of x of n, x0, 2, 4, 6. Here's my n on 2-point DFT to give me x0 for n over 2, k equals 0 to n on 2 minus 1, 0, 1, 2, 3. Here are the odd index values, 1, 3, 5, 7. The big x1, 0, 1, 2, 3. And here are my xk. So x0, right, for x of k if k equals 0, is x sub 0 of 0 plus w sub n to the 0, x1 of 0. So here's x0, here's x1, here's my w sub n to the 0. Multiply that, add them together, and that gives us x0. And then for each of the other values of k up to 3, it's the same thing. We're just adding up these values of different scaling constants. And then as we get into the second half, right, the values of k larger than n over 2, we just cycle through these 4 outputs from the 2 half-length DFTs again. The only difference is that now these constants are different values of w, right? So these are all different values. But this picture sort of shows how we construct these big N values from 2 sets of big N on 2 values with these twiddle factors applied. And this crossing structure is the classic thing you'll see in descriptions of the FFT. Okay, so now we can I think that gives you a pretty good grasp on what the calculation actually involves. Yeah?
I understand how the odd x of 1, x1 of 0 goes up to x of 0. But
Yeah.
how does it go to x of 4?
Yeah, okay. So what's going on here with x of 4? So if k equals 4, then we want x0, so n is 8, so n on 2 is 4. So you want x0 of 4. Now x0 is an n on 2 point DFT, so it's a 4-point DFT. So we'd normally only define it for 0, 1, 2, 3. So here I've put in here, but what happens if you actually take the equation and plug in k equals 4, well, w sub 4 to the 4 is just w sub 4 to the 0. So it turns out to be the same as doing it for 0. And so here I've specified that, well, I'm actually going to use modulo indexing. That basically, once I get above n on 2, I just start back at 0, and that gives me the right result. And so here I'm saying, well, x of 4 is x0 of 4 mod 4, which is x0 of 0, plus w sub 8 to the 4 of x1 of 4 mod 4, x1 of 0. So here's x0, right? With x of 4, it depends on x0 of 0 and x1 of 0, and then here's my twiddle factor, which is w sub n to the 4, w sub 8 to the 4. So it's the same thing. I mean, that's the slightly weird thing, right? These things are not mirror images of each other, because these twiddle factors always come from the lower half. In the top half here, they're the ones that are coming in at an angle. In the bottom half here, they're the ones that are coming straight across. But it's because the twiddle factors are always applied to x1, so they always are they're always being applied to the arm that comes from down here. Okay? Yeah. All right, so that was like, we broke it in half and we saved half the computation. But what we ended up with was two smaller DFTs. What we just did was figure out how to take a large DFT and calculate it with fewer calculations. Can't we just do that again? So can't we take our n on 2 point DFTs and then decompose those into even smaller DFTs and then save calculation again? Well, yes, we can. So we could say that, well, if x of k is equal to x sub 0 plus something times x sub 1, then we can take x sub 0 and decompose that. This is an n on 2 point DFT. We can decompose it into two n on 4 point DFTs, x sub 0, 0, and then w sub n on 2 to the k, x sub 0, 1. This would be the n on 4 point DFT of the sequence formed as the even indexed values of the sequence formed as the even indexed values of the original sequence. So sort of doubly even here. And this is an n on 4. This is the n on 4 point DFT of an n on 4 point sequence, which is the odd index values of the even index values of the original sequence. So slightly, we can figure out what those are, but it's slightly weird to think about what it means. And then we can do the same thing for x sub 1, the n on 2 point DFT, as these two n on 4 point DFTs. And basically, now we've taken our original sequence and we've broken it up into 4 subsequences depending on whether they were even or odd values in, at two levels. But basically, we've now done the same thing, that we had two n on 2 point DFTs, and we've calculated them as 4 n on 4 point DFTs. But basically, we've got another factor of 2 saving because, we've got n on 4 squared times 4, so we've saved an overall factor of 1/4 in the calculations. What does that look like? Well, here's the flow graph we had from before, where we take these two 4-point DFTs and then combine them to get our 8-point DFT. But here now we've replaced our two 4-point DFT structures with 4 2-point DFT structures in this case, because n on 4 is 2. And here's our same kind of twiddle factor arrangement for these two pairs of n on 4-point DFTs, right? So it's the same thing. We have each output point as the combination of the corresponding points from the two halves, and then we've got the twiddle factors applied to the lower half in each case. And the same thing down here. And now these are these subsequences, right? So before we had x0, 2, 4, 6. So the two even index values were 0 and 4. So now they're up here. And the two odd index values were 2, 0, 2, 4, 6. So now 2 and 6 are the odd index values, and they're down here. And before we had 1, 3, 5, 7. So 1 and 5 are now the even indexed values of the odd index sequence. And then 3 and 7 is the odd index values of the odd index sequence. So our output is nice and in the correct order. But to make this diagram, avoid having crossed lines, our input sequence has ended up in a somewhat shuffled, garbled order. But, you can see the structure here, and you can more or less figure out what's going on. Of course, now we can keep doing this. Like every time it's like, oh, well, we're just decomposing into shorter DFTs, so we can just do this again and again and again. Eventually, we get down to very short DFTs, which is actually what just happened for our 8-point example. That a 2-point DFT, we can't decompose it any further because a 2-point DFT is a pretty trivial operation. It's just one output is the sum of the two inputs, and the other output is the difference of the two inputs. That's what you get if you W sub 2 is just -1. So this would be, in our previous diagram, now we would just replace those DFTs with just these simple adds. They're multiplies, but they're multiplies by 1, so they don't even really count as multiplies. And so as long as we have a length that we can always keep dividing it on 2 until we get down to 1, then we can do this and get down to these. That would mean the original length was some power of 2, right? It means that it was, well, we could halve it and halve it and halve it and halve it. So that'll only work for something that's 2 to the m. But if we have n equal 2 to the m, then we can do m stages of dividing the DFT lengths in 2. And basically all the DFT calculation disappears because it just reduces down to these sums and differences. And the only multiplications we're left with are the twiddle factors, right? Are the little w sub n to the k's that we have to use when combining the even part with the odd part. So the real multiplies, if we work it all out, and now instead of being order 4n squared, or 4n squared I think it was, it's now m times 4n, where m is the log base 2 of n. The real adds, again, is proportional to m times n. And so the complexity is this order n log n, which we spoke about at the beginning, specifically n log 2 of n. And that's a big win compared to n squared, particularly for large n. So that's the big, that's the magic of the FFT, that we, by doing the successive decomposition of the problem, we only had to decompose it by the number of times we could decompose it was proportional to the log base 2 of the number of points we came up with. And at each stage we got this saving, and so we end up with a significant reduction in the complexity. And the amount of reduction basically depends on how many stages we can add, which is proportional to log of the original length. Given that we're trying to absolutely minimize the computation, we can afford to spend a little bit more time analyzing this, and there are a couple other tricks we can think about. So one is that, well, this is kind of, if we pulled out one particular pair of outputs from the odd and the even index parts, this is the structure we get. We get the even index part goes straight through, gives us that thing, and then it goes straight through and gives us that thing plus n on 2 in the second half. And the odd index part, we have one twiddle factor and we add it in here. Then we have a different twiddle factor and we add it in here. But the different twiddle factor here is, it's the second half. It's like n on 2 twiddles further on this one. this factor here, w sub n to the r plus n on 2, well, w sub n is just e to the minus j 2 pi on n, so w sub n raised to the power of r plus n on 2 is e to the minus j 2 pi on n times r plus n on 2. We can distribute over that sum, so it's e to the minus j 2 pi r on n times e to the minus j 2 pi n on 2 on n. But this thing, we cancel out the n's, cancel out the 2's, it's just e to the minus j pi, which is just minus 1. So it's just, and this is of course just w sub n raised to the power r. So w sub n to the r plus n on 2 is just the negative of w sub n to the r. And so we can have the same calculation. This involves two complex constants, two complex multiplies. Here we just have one complex multiply, which gives us the right value here. And then we have to flip its sign to give us the right value for here. But that's OK, because flipping the sign is just replacing our addition operator with a subtraction operator. So basically, we can also halve the number of twiddle factor multipliers we can do because of this structure, this relationship between them. They're different values. This is, we take our two half-length values, we twiddle one of them, then we take their sum and difference, and we get the unique values that we wanted. So that's another halving. And then finally, of course, for some of these values, r is equal to 0, which means that w sub n to the r is just something to 0, so it's 1. So if we're able to look at it that closely, then we can eliminate those values altogether. So this is a fully optimized 8-point decimation in time f of t flow graph. Here are our numbers in their strange shuffled order. Here, so these are 2-point DFTs, which is just like adding and subtracting. Here are the twiddle factors. I've eliminated the r0 and the r equals 0, w sub n to the r, and w sub n to the, well, they're both the w sub n to the r values. And so here's the remaining twiddle factor, just 1, and then we have this thing where we add to get the first 2 and then subtract to get the second 2, which is, getting our w sub n to the r plus n on 2's. So this is the output of the 2-point DFTs. This is the output of the two 4-point DFTs. Then here again, we've got a set of just n on 2 minus 1 twiddle factors, because this one is the 0 one which disappears. And then we add and subtract, and we get our 8-point DFT coming out. So now we've basically got an 8-point DFT with 5 complex multiplies, 5 coefficients and 5 complex multiplies, instead of, whatever it was, n squared, 64 or something. To implement this, we need to make sure the sequence is in the right order to begin with. And it turns out that if we actually figured out what we did, which was basically taking, the even and odd parts of every even and odd sequence, if we write down the binary representation of each of these indices, right, 0, 4, 2, 6, etc., these ones are going to be the ones that were odd numbered, so they're the binary numbers that have 1s at the end. This is actually just binary counting, but with the bits in reversed order. So this is called bit reversed indexing, which is what you get if you want a binary, a radix 2 f of t, and f of t where we're talking about dividing the blocks into 2 every time. You can quite easily write an algorithm to to reorder your sequence to be in this order simply by taking each point and swapping it with its bit reversed version, as long as you only hit each point once, else you'll swap them twice and you'll end up with the same thing. And so when you've done that, then you have this very kind of nicely structured and well-organized flow graph, which actually, suggests an algorithm, which is basically you just have big N memory locations, and then this is the flow of operations that you have. This sum and difference operator, which you do with on adjacent points here, that gives you this stage. Then you go in and you apply your twiddle factors. Then you have this sum and difference operation, which you apply on points that are separated by 2. Gives you this stage. You apply a different set of twiddle factors, so you've got to write some logic to make sure you do the right twiddle factors. then you finally have the sum and difference operations strided by 4. But you can do it in place, which means you don't need separate memory locations for the input and output. You can reuse the same memory locations. And if your memory budget is a big deal, then that's nice to know. So this is basically what, if you actually look inside an implementation of an FFT algorithm, this is what it's going to be doing inside. This is very, very literally the algorithm that is implemented. And if you have it implemented in hardware, which of course is sometimes something people want to do, then this is what the structure is going to look like in hardware as well. So the biggest limitation on this, in order to realize this saving, was that we had to be able to divide the actual length of the DFT by 2 and get integer values multiple times. So we had to have n equal 2 to the m. And when we do that, we're calling it a radix 2 FFT. Radix is somehow the number base for this FFT operation. But it turns out we're not limited to using n on 2. Using radix 2. The 2 is that the very first thing we did, which is when we said, okay, we're going to take this set of n values and we're going to take them in pairs. We're going to take them in groups of 2. So we have the even and the odd indexed parts for each step. But we could have taken them in 3s. If we'd had an n which was a multiple of 3, then we could have taken it as n on 3 summations over, a value that's indexed by a multiple of 3, a value that's indexed by a multiple of 3 plus 1, and a value that's indexed by a multiple of 3 plus 2. We don't really have names for, equivalents of odd and even for multiples of 3. But it all works out the same as long as n is divisible by 3. And then we end up with 3 n on 3-point DFTs and a corresponding saving. And so that would be a radix 3 DFT, which is directly analogous. That doesn't have huge applicability. But n equal 4, radix 4 FFT is kind of interesting, because even if you're working with radix 2, then if you've got 2 to the even number, then you can also break it down as 4 to the even number on 2. And you can make each of your elemental n on 4-point DFTs, now you're going to have some, it's not going to be just adds and subtracts, but because w sub 4 is just minus j, it still actually doesn't involve multipliers, it just involves swapping the real and imaginary values in a Cartesian representation. And so you can have it as straight line code, so you can make it more efficient. So radix 4 is sometimes you see that because it'll allow you a little bit of extra optimization. If we had a number that wasn't some basis, some radix to the power to some power, but let's say we had a composite number as our length. Well, if we've got this way of breaking down, a DFT into 3 n on 3-point DFTs, we could actually have something where the first stage is breaking it into 2 halves, but then these halves are multiples of 3, so break each of those halves into 3 thirds. There's nothing about this analysis which says you have to use the same decomposition of the DFTs at every stage. So you can use different breakdowns if you have the implementation for them at every stage. So you can have these mixed radix FFTs, and so that'll actually give you for an arbitrary value of n, you can try and get the best FFT type speed up by figuring out what the factors of that size are, and then doing each of those different radix decompositions at each stage. And this is actually what MATLAB does when you call FFT. I'm not quite sure. It probably has special case for a few small values, and then for larger values it somehow builds those DFT stages on the fly. But it will try and when you calculate DFT, which is the command is FFT, it will do a mixed radix FFT. Of course, sometimes if you have a sequence which happens to be some arbitrary number of points long, you may not be worried about getting exactly the DFT. It may be like if you have a DFT which samples your DTFT more finely, you'd be okay with that. So it's very common to just take some arbitrary length sequence and then pad it out to the nearest enclosing power of 2, and then just do the radix 2 FFT on that length. In many libraries, a typical library will only implement radix 2 FFT, so it has to be a power of 2 that you pass in. But zero padding just means you have a little extra resolution in your FFT, in your DFT, which is often okay. All right. Any questions about that? Yeah.
So is MATLAB using radix 2 as well?
If you pass a sequence which is a power with a length as power of 2, it'll use radix 2. Yeah. So I can't tell whether. So one thing, if I have, n equal 32, say, then I could do that as 5 stages of radix 2. But I could also do it as 2 stages of radix 4, 4 times 4, and then a radix 2, right? So if I had a radix 4 available and it was faster than doing 2 stages of radix 2, then I would be better off doing 2 stages of radix 4 rather than 4 stages of radix 2. And so I'm not sure if MATLAB, it doesn't necessarily have to use the lowest factors. It can use the largest factors for which it has efficient implementation. So I'm not sure how it does that, but it does do the actual full implementation. I mean, at some point you're just calculating n-point DFTs for some n, and even though you may be able to break it down, there's some crossover point where the twiddle factors are, and just the extra, the convoluted logic flow mean that it's just simpler to actually do the straight up naive calculation of just the n squared calculation. And so, it totally depends on the details of the implementation, which of those is faster, but you can try and make sure that you always use the fastest one. Okay, let's just look at some of that in MATLAB just to sort of make it real. So in today's here we go. In today's MATLAB diary, there's some examples of this. And so what I'm going to do is I'm going to take just an arbitrary piece of signal. I'm going to read in this old sound file we had before, but it doesn't matter what it is. I can take the FFT of a 32768 chunk of that. 32768 is 2 to the 15, so it's a power of 2, so it's fully radix 2-able. But then I could also take something which is almost the same length, 32767, it's 1 point shorter. We can take the FFT of that and see what the difference is. So let's just try those. These are values from my laptop of 2 generations ago, so they're much smaller now. Okay, so this 32,000 point FFT is taking 0.5 milliseconds, 482 microseconds. But if I do the same thing, so tick and tock are just MATLAB commands that read the system clock and tell you what the difference is so you can time an operation. If I do it for 1 point less, which is actually less computation, right, I'm getting fewer points out, then this is now 2.4 milliseconds is the best we get. So it's actually like 5 or 6 times slower for a shorter sequence just because it can't realize the radix 2 gain. But actually it turns out that 32767 is not prime. It's 7 times 31 times 151. It's got some fairly large prime factors, but it's not exactly prime. The largest prime number that is smaller than 32768 is 32749. So if we do the same thing here, 32749, which is again even shorter, then this is a little bit slower. It's like, it's only maybe 30, 40% slower. But it is actually, because there's no, the only way it can do that, there's no FFT decomposition. It just has to calculate the full n squared calculation. Then we get this thing slower. Just to make the point that the FFT routine is highly optimized, we can actually do this calculation directly, right? So there's a MATLAB command which is DFT matrix, which calculates the n by n matrix that you'd use to calculate a DFT. So this is, for a 4096 point DFT, which means we get 4096 frequency values for 4096 input values. Then here's our n by n matrix. If we actually look at if we look at some sub-range of that matrix, so we look at it's a complex matrix, so we look at the abs of dm, the top 100 squared points here. Image SC. That's interesting. That doesn't look very good. What if I do the whole thing? Why did that happen? So if each row of dm is just this, these basically the sinusoidal bases. So if I plot the first row, then it's just constant, right? The first row is 1, 1, 1, but the second row is okay. I plot the abs of that. Oops. Not the abs, the real part, because it's just the magnitude is 1. That's why it looked weird. Yeah. Okay. Then I get sinusoid. That's what I want to do. I want to do the image SC of the real part, and then you see these nice little. That's kind of interesting, but they're. They're basically these. This is like the first sinusoid, and then these are increasingly high frequency sinusoids. So now we see the oscillations, the period getting shorter and shorter. That's kind of what this is just the top left hand corner of that DFT matrix. But this is what each row is a sinusoid at increasingly high frequency. So then the DFT calculation is. X of k is the matrix times the vector. In this case, it's only a 4096 point thing, so let's do that. And that's calculated essentially the same as the FFT of D104096, I think. So the max of the abs of x minus xx. Yeah, so they're the same. The difference is tiny. It's giving me the same calculation. But if I look at the computation time difference between those, I don't know if that's going to work. Let's try this. Tick, tock. Yeah, so this multiplication is taking like 18 milliseconds, whereas this FFT, let's see, this is a very short FFT, right? Yeah, it's taking like 80 microseconds. So that's, let's see how much faster that is. Yeah, so it's 200 times faster to use the built-in FFT routine than to do the actual matrix multiplication, which is what it amounts to. But of course, this 4096 point FFT is not calculated by this n squared matrix multiplication. It's doing the radix 2 and speeding it up, as well as not having to actually use a general matrix multiply, but can have the whole thing optimized. So you get a very big win from using these FFT routines. Any questions about that? While we're here, so the remainder of this slide pack is Oh, let's talk through this. Okay. While we're here, though, while we're in MATLAB, some of you may be going to use the FFT in your projects to look at some spectra. And so just a few things I'd like to show you about how you can actually plot spectra in MATLAB. So if we have a signal, we want to take its spectrum, maybe we just want to plot it. Let's see what happens then. Okay, that's what we get. Okay, now what happened was that the sequence we passed to the plot command was a complex sequence, right? It was complex value. And so MATLAB says, oh, you give me a complex value, you ask me to plot it, I guess you must mean you want me to plot the real part against the imaginary part. So it takes this, end-on view of our sequence and just plots them as the real part versus the imaginary part, which is not what we wanted. What we really wanted was to know the, say the energy at every frequency bin. So then we want to send like plot of abs of this. Okay, and that gives us now a function of our 32768 bins in our FFT and their magnitudes. It looks like this. And this is saying that, here in low frequency there's some energy, and as frequency goes up, the energy is less, which is typical of a speech signal. This is a piece of speech, has most of its energy in the lowest frequencies. But then we see what comes along here is that now we see this energy going up again at the very high frequencies. What's going on there? Yeah.
But that signal is a real signal.
Yeah.
Signals are always symmetric DFT.
Thank you. Great. So what it is because it's a real signal, it has a symmetric DFT, which means that this is basically k going all the way from omega equals 0 through to omega equals 2 pi. And this is the negative frequency part that we would normally think of being over here, coming up just before we hit omega equals 2 pi. So this part is, for a real signal, it's always going to just be the mirror image of this part. And so really it's not interesting to plot. So what we really want to plot is abs of SD for 1 to length SD on 2, right, the first half here. And now that's much more the spectrum that we expect. And now it's giving us the 16384 points, which are the half. Now, normally, we're fond of looking at these magnitudes in a log scale, in a dB scale specifically. And it looks kind of different here, right? So now the values are, from plus 40 dB to minus 60, and we see a lot more structure in the high frequency because the high frequency was only, 30 dB, only like, 1/30th or something of the peak energy, so we can see what's going on. And these may be important to us because that's audible. That's why we care. If we remove these frequencies, the speech would sound very muffled. We've got a lot of points here. I've got 16,000 points, and so there's a lot of jumble. If we zoom in, then we can see it's a little better structured. But a long DFT will give you a lot of detail like that. The other thing is that now here the x-axis is in terms of k, in terms of the DFT bins. Very often we might want that actually to be the actual frequency. If we've got a sampled signal with real frequencies, then we might want that. So then the actual number of points here is 1, 2, it's 16384. But the frequencies they correspond to are, 16384 is going to be the highest frequency, which is the sampling rate on 2. So we can actually convert those into the corresponding frequencies by normalizing them by 16384 and then multiplying them by the sampling rate on 2. And now we get a plot where this is now in hertz, right? This was 16 kilohertz sampled speech. So now we've got the spectrum in terms of hertz and the dB level. And so if we have a question like, well, what is the magnitude of the strongest component here, we can zoom in and we can say, oh, look, well, it's actually... this is not such a great example because it's a long piece of speech, so it didn't have clear periodicities in it. But there's a peak here at like 480 hertz or something like that, and that's what we're seeing. Yeah.
So now we don't get very good granularity. like zero padding in the end,
Yeah.
you get more frequency bins, and could we zoom in on like 405 or something?
No, you see these values, right? So you're saying, well, look, the labeling here is only 400 or 500, so it's not very good. But we can see the values are much finer. That's just the labeling. The actual values here, we took this 16,000 point FFT, and so we've got a resolution, which is, we took the 32,000 point FFT. We've got a resolution, which is sampling rate, the length of the signal, the sampling rate divided by 32,000, right? So we've actually got 0.5 hertz resolution, or 0.1 hertz resolution, or something like that here. Is that right? If I zoom right in, you can see these individual points. And yeah, they're sort of, they're roughly 1 hertz resolution. If we had a shorter signal, and so if I just took if I took, the X is the FFT of some 256 point signal, say, and try and plot that. So now I really do want it to be length of X divided by length of X times SR on 2, and then, wait. I'm screwing this up. If we, okay, let's call that SD, and then plot our dB of this. So now we've got something where we've got many fewer points in here, right? So if we zoom in around here, then we sort of have, just, these are, again, bins, but we see that they're kind of, they're crudely, they're fairly coarsely sampled. We could do this thing of taking a much longer DFT. So I could just do D padded with zeros, 16384 minus 256. Horizontal, vertical cat, and then for comparison, I can plot that. Did I do this right? dB abs, not SD, but X2. And these are actually looking at the same thing, right? So you see this valley in here is corresponding to this valley here, and they're sort of following each other. They're not quite the same length just because of the scaling here. Let me just quickly show you this. So if we plot these against real frequencies, so this is 8192 divided by, essentially, technically it's 0 to 8191, right? Because the bottom bin has frequency 0 times SR on 2. Right, so this is 0 to 8,000. And then if we did the other one, the first one, the same, but now it's 0 to 255 divided by 256 times SR on 2. Length SD on 2. What did I do wrong? Because it's 128, 127. Okay, so now they're on the same frequency axis. Now if I link axes, so they scroll at the same time, then if I zoom right in here, you can see how these individual sort of kinks here have now been rounded out, that basically I've oversampled this FFT, this DFT domain. I've sampled it much more carefully. Now, because it was a short signal, all the features are kind of blurred out. They're blurred out, as it were, by the rectangular window. So it's like we had some line spectra, but we've convolved them with these nice, sync functions. So we see, but here, just by doing the zero padding, we can see exactly, where the local maxima were. Is that what you were asking?
Yes, but just the last sentence. So,
Yeah.
What can you still read from the bottom picture, or is it just noise because we open?
Let me just see if I can plot these on top of each other. So hold on. Plot of that and use red. and hold off. Oh, man. Damn. Hold on and plot of this one. So it should be that actually these red points are samples of the blue curve, because the DFT samples the DTFT, and so what we can see is that the actual samples that we got on the coarse representation, they're correct, because we could have just calculated one from the other by taking the red signal, taking the IDFT, and then taking the longer DFT. But it's actually saying that we kind of missed some of these peaks, that actually if we tried to measure the frequency exactly in here, there was some energy in here, but it was sort of midway between two of the coarser bins. So by getting to this higher resolution, we actually got a better description of what was going on in terms of the frequency content. You see, that's the red line is not such the blue line is pretty much what the DTFT would look like. And the red line is like this sampling of the DTFT by the DFT, and it sort of doesn't do such a great job. It misses out some of the structure, misses out some of the detail. All right, great. Any more questions? All right, have a good Thanksgiving, and I'll see you on Monday.